Alright, we'll do a quick debrief to the structure elucidation by combined techniques class exercise, which we all did last Friday. Okay, so we'll begin with the first question. Okay, so the first question, you were told that there are 4 elements given to you, C, H, N, and O, and you're given the mass spec and the NMR. And of course, the integration ratio for each of the signals in the NMR is shown. You were told that the resonance at 7.9 disappeared on the addition of D2O, so that probably tells you that that is due to a protonic hydrogens. So either bonded to OH or NH, either NH or H2. But of course, if you scroll down, integration ratio of 1, so probably not an NH2. Okay, so we can just erase this off. Okay, mass spec not very inspiring because you're not really given the exact mass charge ratio. Of course, you can determine it from the line. So you have a base peak at 108. Okay, if you just do a quick count, and then this at 109, and then the molecular ion peak very close to 180, so that's 179, and then there's also a prominent one, that's 40, 41, 42, 43, that's 43 here, and then you have one here at about 137. Okay, so probably these are the few peaks. If you want to, you can try to determine what they are. Yeah, if not, probably we should focus on the NMR signal. So for the NMR signal, right, you are given essentially the integration ratio, and that kind of like gives you the total number of protons that the compound might have. So you get 1, 2, 2, 2, 3, 3. So if you do a quick calculation, you get a total of 6, 7, 8, 9, 10, 11, 13. So 13 H's. Okay, and let's see what other data we can tell. Okay, so this is likely due to the protonic hydrogens. Okay, and I'll change to another color. Okay, so we have a very prominent ones here, quite symmetrical. So and the chemical shift is about 7. So we are expecting it to be a 1,4-disubstituted benzene. Okay, so we are probably looking at a structure that looks like this, an X here and a Y here. Okay, something along those lines, and then maybe the protonic hydrogen is in either the X or the Y. Okay, and of course, another extremely prominent signal here would be that at 4 ppm. Okay, so that's a quartet. There's a quartet here, and then we have one here at close to 1.4 ppm, maybe they're about 1.4 ppm. So that's a triplet. Yep. So this kind of like allows us to combine these two. Okay, maybe this can give us some clue to what they are like. So it's likely to be a CH2, CH3. Okay, next to a highly electronegative element. And of course, having an integration ratio of 2 here does correspond to this. Integration ratio of 3 here corresponds to this. Okay, and if you check your data booklet, for you to hit about 4 ppm, okay, to hit about 4 ppm, this unknown element likely to be an oxygen. Okay, it's likely to be an oxygen. So we're just going to erase off the box. Okay, so this is likely to be the oxygen here. Okay, and then we have a signal at about 3 here, sorry, 2 ppm, integration ratio 3. So this is likely to be a CH3. Okay, if you check your data booklet, it could be a signal next to the phenyl ring, or maybe next to a electron withdrawing group. Okay, so with all the data given to us, we probably want to maybe try to fit all the information up a little bit, because the first thing we need to do here is to determine the molecular formula. Okay, so we'll try to determine the molecular formula by piecing all the information together. Okay, so as we saw from the mass spec, we have a molecular ion peak at 179. Okay, and remember earlier on, we kind of highlighted that we are going to get a 1,4-disubstituted benzene ring. So this portion gives us C6H4. Okay, so we're going to subtract it off from here. So 6 times 12 is 72. 72 plus 4 is 76. So we have 76 here. Okay, and the next thing we're going to do is, okay, over here, we have a CH2, CH3, and we are quite confident. Okay, remember, we are quite confident that it's an OCH2, CH3. Okay, but however, let's put that aside first. So let's just subtract maybe 29 from here. Okay, first. And then, what other data do we have? Okay, we have a CH3 here. Okay, so that's minusing off another 15. Okay, subtracting off another 15 here. And let's see what other things we can find from here. Okay, so we have an N because the question tells us that we have an N, and it's likely that we have a protonic hydrogen next to a nitrogen. Okay, why are we so confident that we have a protonic hydrogen next to a nitrogen? Because you can see from here that the oxygen is already used to bond to OCH2, CH3. So in this case, we are definitely not going to expect an OH somewhere. So in this case, we're going to just minus off maybe an NH combined. So that's another 15 here. And then, of course, we're going to minus off a 16 due to this oxygen. Okay, right. So okay, right now I'm going to take a calculator here. I'm going to punch some numbers. So we're going to take 179 minus 76 minus 29 minus 15 minus 15 minus 16. Okay, that gives us a beautiful number, 28. Okay, now 28, it's a relatively unique number, I have to say, because it's an even number. Okay, now think about it. What are we left with? Okay, what are we left with? Because we have utilizes all the hydrogens, largely, there can't be any more hydrogens. We have utilizes the N, so could there be another nitrogen? Or could this be two nitrogens? Is it possible? Okay, I would say highly unlikely. Okay, highly unlikely. Or could we be looking at maybe 2 carbon and maybe 4 more H, but earlier on we already say no more hydrogens. Yeah, so normally 28, right? If you're sharp enough, you'll be thinking about a C double bond O. Okay, a C double bond O. Okay, why are we so confident about this? Because if you shift back here, right? If you look at a 43 here, okay, if you look at a 43, okay, I'm going to change another color. So a 28, okay, if you subtract 43 from 28, okay, you're going to end up with 15. So just nice, because over here, did you realize that we have a CH3? Okay, so it is likely that part of the structure, right, part of my structure contains a methyl ketone. So like this, and a CH3 somewhere, which potentially give rise to a singlet at about 2.1 ppm. Okay, so with all these information, I'm going to use an eraser to erase this portion so that I have some space to write. So we started off by postulating maybe a phenyl ring, okay, a phenyl ring somewhere, okay, with an X and a Y here. So can we just postulate maybe a O ethyl group here first? Maybe a O ethyl group. Okay, and we know that we need a CO CH3 and we need an NH somewhere. So if you piece out all the information, the only place where the NH can go will be here, and then the COCH3 can go will be here. Okay, so this is the only place it can go to. You can't really have other combination. Yeah, because in the course of marking, I think some of the students, let me just erase to get some space here. Some of the students were thinking along something like this. You have a O ethyl, and then you have a carbonyl here, and then an NH like this. But this particular CH3, right, is likely to give you a chemical shift of slightly above 2.5 or close to 2.5. Okay, and most importantly, you will not be able to get this particular fragments. Okay, so yeah, so with that, I hope you can kind of like see, you know, like how how we learn to piece up information together. And what about the what about the one H? Sorry, not one H. What about the mass spec? Okay, what can we do about mass spec? Okay, so for example, if you are looking at, let's say, 137. Okay, what can 137 be? Yeah, so that's the difficult one that some of you face lah. Yeah, so I have to say that for this particular mass spec, it could be a little bit beyond most of you. The reason being they involve some form of McLafferty rearrangement. Okay, so yeah, it's a little bit unfair, but yeah, I mean that's how it works here. So if I'm just going to erase this, and I'm just going to show you some of the thought process in getting the fragments, right. So remember that we were proposing this O CH2 CH3, right, and then we have NH, okay, and double bond O, and CH3 here. Yeah. So potentially, can we force out some form of McLafferty rearrangement? Yep. So that is how it works. Okay. So sorry. Let me. Okay. So the arrow push is going to be like this, and like this. Okay, so in this case, because if you take a look at 179 minus 137, right, this is actually a M minus 42 peak. And if you look at my McLafferty, this portion, right, okay, I am actually subtracting off a CH2CO. A CH2CO, this is 14, this is 28. So in this, indeed, I'm getting M minus 42 for 137. Okay, so I'll leave you guys to think about how can we actually get 109. Okay, are we able to get some form of McLafferty rearrangement for 109? Okay, so the success of this question is not so much about elucidating or trying to decide what your mass spec can end up with, although I think the teachers, we do feel that maybe this particular question is a little bit unfair, but I think the success of this question is largely based on how sharp you are at looking at the NMR data. Okay, yep. So without further ado, I'm going to move on to question 2. So I think question 2 is slightly more inspiring because we do see quite a number of more people getting the answers. Okay, so yeah, we have an unknown drug. It's a non-steroidal anti-inflammatory drug. Wow, that's quite mouthful. Okay, so used to relieve symptoms, arthritis and fever. Okay, and of course, in this case, you are in quite safe zone because you are given the molecular formula. So if you are given the molecular formula, you can easily calculate the degree of unsaturation. So that's 2n plus 2, that's 28 minus 18 divided by 2. So you're going to get 5. So I think you can safely assure that 4 of it is due to the phenyl ring. Okay, and then you can see a very sharp C-double-O stretch, and of course this particular region, as well as this particular NMR signal, you can confirm that you have a CO and it's likely to be due to a carboxylic acid. Okay, so yeah, so I'm going to erase this. I mean, to make it clearer. Okay, so yes, so the first thing I need to be able to elucidate out from here is probably a carboxylic acid somewhere. So, and a carboxylic acid has to be found right at the end. So I'm just going to draw it out over here. Okay, next I'm going to look at a 1H NMR. Again, 1H NMR. Again, we don't want you to decipher the individual signals, so we just give you everything as a multiplet. Chemical shift between 7.21, I mean 7.09 to 7.21. Integration ratio 4. So likely to be a 1,4 disubstituted aromatic, I mean benzene ring as well. So I'm looking at a system that could is an XY system. So in order, I mean, it can be 1, 2, 1, 3, or 1, 4. It doesn't really matter, but I prefer to write it as 1, 4 because it gives me a bit of space to write things. Okay. Then the next thing that we thought that we can we can easily share with you is there are two pieces of information where you can actually kind of pair them up. Okay, it's actually over here. Can you see that you have an integration ratio of 6, 0.89? 0.89 actually tells you that the methyl group, likely to be the methyl group, okay, it's right at the end, it's a doublet. Okay, it's a doublet. And then we have 1.84, which is integration ratio integral 1.84. It's a multiplet. Okay, so with this, you can actually pair up these two. The reason why you can pair up these two is because this actually gives you a very characteristic um, structure. Okay, with a 6-1. Okay, it tells you that it's some sort of an isopropyl group. Okay, so we have a CH3 here, and then a CH, and then another CH3, and then bonded to, likely bonded to be to other things. Okay, now well, this other thing, right? Will it be able to split this up further? Well, may or may not, because they kept it open here. They call it a multiplet. So maybe it can split it up further. You never know. However, if you look north, okay, if you look north, you notice that at about 2.44, okay, there is a doublet over here. Okay, there is a doublet over here. So 2.44, there is a doublet, and integration ratio of 2. Yeah, so this actually gives you a very important clue. How do you actually get this doublet? This doublet must be due to a nearby CH, this particular nearby CH. And 2.44 is actually relatively deshielded. So instead of putting a question mark here, shouldn't I continue by putting a CH2 here? Correct? And this is a clear doublet, it's a sharp doublet because they didn't tell you that, you know, it's like ambiguous or what. So, and 2.44 is likely to be characteristic of a benzylic system. Okay, you may be thinking, well, I mean, it can be C double bond O, it can be this, it can be that, but however, based on the formula, the COOH is already taken by the carboxylic acid, so you can't be thinking about other electron withdrawing system besides an aromatic ring in this case. So therefore, in this case, I will propose an aromatic ring directly. Okay, so with all this coming into the picture, right, my final portion here will be an unknown, correct? So can I just bond to a carboxylic acid directly? Well, I mean, there are several things you can do. Okay, so the first thing that you know, like I will advise the students is to subtract the thing off. So we have C13, H18O2, right? Okay, so I subtract this portion off. So this portion have 1, 2, 3, 4. 4 plus 6, that's 10 carbon. How many H do I have? 7, 8, 9, 10, 11, 12, 13. 13 H. And then any oxygen? No. So when I subtract them off, I'm left with, sorry, I'm just going to write this out properly. C3H5O2. You notice that? Okay, then I'm going to move on further. I'm going to subtract a COOH, CHO2. So I'm left with C2H4. Okay, so therefore, what this whole thing is trying to tell you is that instead of this question mark, I am actually bonded to something, an unknown box, and this unknown box is likely to be bonded to a carboxylic acid group. And of course, this unknown box is C2H4. Okay, now let us go back to our 1H. So the final portion where we haven't elucidated or we haven't find out anything is actually these two things. I'm going to highlight in yellow. Okay, so it's here 3.67, which is a quartet, 1.47 integration ratio 3 doublet. Okay, now people check out the integration ratio is 1 and 4. So it's total of 4 protons. So it matches this data. Okay, of course, 1H doesn't tell you carbon. Okay, so how do you end up with a quartet and a doublet in this case? Well, I mean, it needs, I mean, no further deduction, right? For you to have a signal at 3.67, which is quite disputed. I must be probably next to two highly electron withdrawing groups. Definitely not oxygen here because we can't have oxygen. So in this case, I would propose a CH. And then by one more bond, there will be a CH3. Okay, and then this is a perfect match already because this hydrogen will be splitted into a quartet by the CH3, which is reflected by this particular multiplicity. And then this particular CH3 will be splitted into a doublet by the H, which is reflected by this. Okay, so with all this, I hope you can see how we can go about doing structural elucidation. You know, structural elucidation is not any old how. So there is some logic flow and then a bit of trial and error here. And I hope that you find this debrief beneficial, and then at the end of the day, you can apply them into other questions which you encounter.